Yeah. So yeah, today, we're quite happy to have Alan Scheie, who actually has done some really interesting work recently on the triangular lattice quantum spin liquid candidate. He has also done some beautiful work earlier, working on sort of basically entanglement, and it's somewhat of a new concept in the community. So that's why I invited him, wanting him to give a sort of a tutorial, like a talk to the community, so that we can sort of look up to it afterwards. Yeah. So Alan is currently working at the Los Alamos National Laboratory, and I believe he was a former student of Colin Broholm, right? And you did postdoc with at the Oak Ridge National Laboratory.
20 minutes late. I will try to make up time and make sure we get done by the top of the hour. So I think big thanks again to Peng Cheng for inviting me to talk about triangular lattice work that we've been doing. And this is far from just my work alone. This has been efforts of a large number of people that I've listed here on the right. It's a very big collaboration, lots of different perspectives that allowed us to do the work that we did on potassium ytterbium selenide and sodium ytterbium selenide. So next slide, please.
Yeah. Okay.
Okay, so 3 main points I want to make in this talk. If you remember nothing else, this is what I want you to take away. The first point is that potassium ytterbium selenium-2 is an excellent realization of the Heisenberg J2-J1 model and is close enough to a quantum spin liquid to host fractionalized spin-on quasiparticles, at least at finite timescales. The second point is that swapping out potassium for cesium or sodium gives us control over this J2-1J1 ratio. And the third point is that sodium ytterbium selenium-2 appears to be a gapped quantum spin liquid with a 2.1 microelectron volt gap, strongly suggesting that it's a Z2 resonating valence bond spin liquid. All right, next slide, please. So I'm going to assume some background knowledge in this talk, that most of you have heard of what a quantum spin liquid is and are familiar with some of the work that's gone into it. But there's many different definitions of what a quantum spin liquid is, but the one I'm going to be using for this talk is a magnetic state with long-range entanglement and fractional quasiparticles. Now, theoretically, they should exist. It's been shown for certain models of spin interactions on certain lattices with certain Hamiltonians, you get a spin liquid ground state, but they've been really frustratingly difficult to identify experimentally. Next slide, please. So the original proposal for a spin liquid goes back to Phil Anderson, when in 1972, he submitted this paper proposing that for a 2-dimensional triangular lattice of interacting spin half spins, that the ground state doesn't order magnetically. It enters this really interesting type of ground state that's a superposition of all possible singlets, and he called it a resonating valence bond ground state. Today, we would call it a spin liquid. However, subsequent calculations showed that the Heisenberg triangular lattice antiferromagnet actually magnetically orders, and it's got this non-trivial magnetic order called the 120-degree order. So Anderson's proposal was not quite right. Although, next slide, please, he was close, because actually further numerical work showed that when you add a second neighbor exchange that's also antiferromagnetic, and this exchange is somewhere between 6 and 16% of J1, you get a spin liquid ground state. And at this point, everyone more or less agrees that you do get a spin liquid phase here, and it's over some extended region. The precise nature of the spin liquid is hotly debated. It depends on which theorist you talk to. More on that later in the talk. But it's known that there's something really interesting there. So next slide, please. So over the years, having known this, many people have proposed different triangular lattice materials as quantum spin liquids. But there's always many doubts about the role of disorder. And the reason is because it's very hard to tell glassiness from quantum spin liquid behavior. Both cases have lack of long-range magnetic order. Both cases have, a diffuse spectrum in the neutron scattering, et cetera. And so this has made progress very difficult. So next slide, please. And so this has led some people to be extremely skeptical even about the existence of spin liquids in nature at all. So this paper published, Art Ramirez is the last author, argues that in real materials, spin liquids always fail. They don't exist. They always end up in this, what he calls an eminuscent phase. And this is something that I think needs to be taken seriously, because it does seem that for so many materials that were thought to be spin liquids, tiny amounts of disorder will destroy the ground state. So next slide, please. And so I myself was a skeptic, and starting to be skeptical of spin liquids until this new class of materials emerged on the scene, ytterbium-3+ delafoscites. And these have magnetic ytterbium ions that form a really crystallographically perfect triangular lattice that are pretty well separated. And there's a large number of variants of these compounds, and almost all of them show no magnetic order down to 1 Kelvin or lower. And with the crystal field state, you're guaranteed an effective doublet ground state. And so this seemed like a really great way. If there is a triangular lattice spin liquid, this might be where we would find it. So next slide, please. So we got into this game when I was at Oak Ridge. Jia Singh was also a postdoc at Oak Ridge, and he grew this new material, potassium ytterbium selenium-2. And it showed no magnetic order down to 400 millikelvin. And we thought, well, maybe this is quantum spin liquid. So we took a closer look. Next slide, please. And so I'm a neutron scatterer. So one of the first measurements I did was measuring the inelastic neutron spectrum using the CNCS spectrometer at Oak Ridge National Lab. I co-aligned 20 different crystals on these plates, and the data we gathered is on the right. The 3 different panels show 3 different temperatures, and the x-axis is different cuts through reciprocal space, the y-axis is energy transfer, and the color indicates the scattered neutron intensity. All right, next slide. If you're familiar with looking at neutron scattering data, you'll notice this doesn't look like your typical magnetic material. Your sort of conventional magnetic scattering looks like what we have on the left. This is elemental gadolinium, textbook ferromagnet. And in that case, you have these really sharp, well-defined magnon modes. But for the potassium ytterbium selenium-2, what we have instead is a diffuse continuum. And so whatever is going on here is not magnons. Now this continuum, next slide, please. It does resemble the continuum that's measured in the one-dimensional spin chain spin-on signal, which, depending on your definition, is also a spin liquid, and then it's got long-range entanglement and fractional quasi-particles. And so in that case, you have this continuum with a well-defined lower boundary where the continuum ends, and that is similar to what we see here. And so this suggests that what we're looking at is a spin liquid. But we need to be careful. Next slide, please. Because as I mentioned, glassiness is also something that produces a diffuse continuum. And this is an image from an ill-fated triangular lattice spin liquid, also with ytterbium ions. And it turns out that disorder in this lattice was producing a glassy ground state, which was also behind this diffuse spectrum. So next slide, please. I don't know how many of you have read this editorial from Igor Mazin on inverse Occam's razor, but he argues that in science nowadays, because of pressure to publish in high-profile journals and everything, people are preferring the more exotic explanations over the simple explanations, which is the opposite of what scientists should do. So we don't want to say this is a spin liquid just because it's the most exciting thing we can say about it. We want to try to have a really good, confident reason to say it's a spin liquid. So next slide. And so this is not an easy thing to do. And so we tried to approach it from 3 different angles using 3 different sort of tools in our toolbox to analyze this. And none of them individually gives us a knockdown answer, but together they kind of help us to have a clear enough picture that we can have some degree of confidence in answering the question, is potassium ytterbium selenium-2 a spin liquid? So the first tool is entanglement witnesses. Next slide. And next slide. This is something I've been working on for several years now in collaboration with Pontus Thorel and Alan Tennant. The basic idea is that you take some data, and in this case, the spectroscopy data, and then you run it through a mathematical filter, which is the entanglement witness. And this gives us quantum information about the material. Next slide, please. So we've written some works on this. If you're really curious, I point you to 2 reviews which are on the archive. The first one is more of a kind of theorist's review where we do a lot of derivations. The second one, which just appeared on the archive today, you can go to the next slide, is, oh, sorry, there's a little animation. More of a pedagogical review where we're talking more to experimentalists about the meaning and how to go about these kind of calculations and so on. But anyway, here's a quick overview of how quantum Fisher information works. This is a quantity borrowed from quantum metrology, and it defines how precisely an operator O can be measured. And so the equation is shown right there. This is the equation for a pure state QFI. And by the Kramer-Rao bound, this gives us a lower bound on the number of entangled objects, such that if your QFI is big, this requires many, many objects entangled together to produce such a signal. And we can be precise about this with the Kramer-Rao bound. Next slide, please. So the operator O that you insert into this equation can be anything, but for neutron scattering, what we want to define this O as is the Fourier transform S operator. And if you plug that into the equation for quantum Fisher information, you get the equation on the bottom, and click next. Those of you who are familiar with this kind of measurement will see that the equation on the left is equal to the total scattering, the energy integrated scattering at a given wave vector Q. The term on the right hand is equal to the elastic scattering, the the omega equals 0 scattering at a given wave vector Q. Both of these are experimentally measurable, and so your QFI is simply equal to the integrated inelastic scattering at a given wave vector. Next slide, please. So importantly for experimentalists, this was dealing with a pure state. In real experiments, we always have a thermal mixed state because we can't get to 0 temperature. And so the generalization was provided by Hauke et al. In an important paper from 2016, where they derived a non-zero temperature equation for QFI and related it to dynamic susceptibility, shown in the bottom. And it's just an energy integral of dynamic susceptibility weighted by this hyperbolic tangent factor. So next slide. All right, so the upshot of all of this is that quantum Fisher information gives us a lower bound on the number of entangled spins, and it's measurable with neutron scattering. Next slide, please. And by the Kramer-Rao bound, if you measure a system of your normalized QFI greater than M, then your system is at least M+1 partite entangled. All right, next slide, please. A side note, the QFI seems to be related more to quantum critical phases in the theory world. It's been used many times for this. So it's not necessarily a witness of quantum spin liquid behavior. It's just a witness of some degree of non-trivial entanglement. Next slide, please. Anyway, so we took this quantity, quantum Fisher information, we calculated it from the neutron spectrum that we measured, and we found that at the lowest temperatures, we're witnessing at least 4 partite entanglement per spin. Next slide, please. So what does this entanglement witness tell us? Again, this is not a proof of a quantum spin liquid, but this is evidence against trivial glassy phases. And in an indirect way, it might be evidence for quantum criticality that we're witnessing in this system. At the very least, a spin glass where the spectrum is distributed broadly over reciprocal space would not give such a spin-on signal. Right. And another detail, the energy dependence of the inelastic scattering at the K point is definitely inconsistent with the scaling that you would expect for magnons, and we observe some different scaling exponent, again, possibly indicating quantum criticality, but we need a little more theory to tell us whether this exponent is in fact what you would expect for this model. All right, next slide. So thus far for the first tool, entanglement witnesses gives us some important suggestions. It allows us to rule out some trivial unentangled phases. But now for the next tool in our toolbox, which really in my view is the most important one, we have to answer what is the magnetic Hamiltonian, so that then we can say, does this system actually live within the spin liquid phase on the phase diagram? Next slide, please. And so to try to arrive at a rigorous answer to this question, we use 3 different tools to fit the Hamiltonian. First is paramagnetic diffuse scattering, second, nonlinear spin waves, and third, we do a heat capacity expansion to fit the bulk properties. Next slide, please. So method 1, we use this technique called Onsager reaction field theory, which is kind of a new kid on the block for analyzing neutron scattering data. This was courtesy of Joe Pattison, who's at Oak Ridge National Lab. And you can use this to fit the high temperature paramagnetic diffuse scattering. And the downside is this is a classical method, so the overall energy scale is wrong. But we thought this still should be useful in resolving the relative ratios between the different exchanges. And so the exchanges we get are on the right. We fit all the symmetry allowed near neighbor exchanges in this matrix and the second neighbor exchange. And go to the next So if you look at the nearest neighbor exchange, you see that the values on the diagonal, the Heisenberg exchange, are all equal to within uncertainty, and they're 2 orders of magnitude larger than the off-diagonal elements. So this is really isotropic Heisenberg-like exchange. And then if you take the ratio of the second neighbor exchange to the largest of the first neighbor exchange terms, you find a J2, J1 of 0.047, which is really close to the 0.06 or thereabouts you need to stabilize a spin liquid. Next slide, please. All right, so that was one method. The next method we used is to fit the nonlinear spin waves. Now in zero field, there are no spin waves. It's just a diffuse continuum. But at an in-plane field of 4 Tesla, you enter this long-range ordered phase. That's the up-up-down phase. And it also corresponds to a magnetization plateau. That's 1/3. That's an inherently quantum effect. So this is interesting that it's there, indicates that we're really close to this Heisenberg triangular lattice limit. Next slide, please. Yes, so this is an inherently quantum phenomenon. Next slide, please. And so we measured the inelastic neutron scattering in a separate experiment, and this is what it looks like at 4 Tesla. Next slide, please. And then we performed nonlinear spin wave fits to this data. Now, the nonlinear part is important because you need the nonlinear effects to stabilize this plateau phase in and of itself. But doing this, we're able to arrive at a fit to the first and second neighbor exchange with rigorously defined uncertainty. And the results, if you click next, are as follows. We get a J2, J1 of 0.043, plus or minus 0.01. And this is really remarkable because it agrees to within uncertainty with the Onsager reaction field theory fits. So next slide. Our third and final method that we use to fit the Hamiltonian is heat capacity fits. And to do this, we collaborated with Laura Messio at Sorbonne University. She and her group have been using a high temperature expansion method where they calculate the specific heat of the 2D triangular lattice as a function of J2. And because this is a high temperature expansion, it fails below some certain temperature. And so we fitted only the 2 Kelvin data and up and allowed J1 to vary and then found which J2 gives us the best fit. And we can define this chi-squared curve that's shown in the subplot of this figure. And the results, if you click next, are that the J2, J1 is 0.037 plus or minus 0.013, which again is consistent with these other methods. And so to me, this is really remarkable. We have 3 completely separate experiments, 3 completely independent theoretical methods of fitting the first and second neighbor exchanges, and they all give us the same result with an uncertainty. And so this is confirmation that this material is really well behaved and really realizes very closely this 2D triangular lattice Heisenberg model. But it also means, next slide, that this system is not quite within the spin liquid phase. It should be, the second neighbor exchange needs to be a little bigger if it were a spin liquid. And in fact, we should see magnetic order, we just didn't look low enough in temperature. So we did this in another elastic neutron scattering experiment on a triple axis. We did see the onset of Bragg intensity, very weak, but still measurable at 290 millikelvin. And in heat capacity, we saw a little blip, a very tiny amount of entropy, but still there at 290 millikelvin, indicating very weak magnetic order. So everything's consistent. This material is a J2, J1 Heisenberg antiferromagnet that's very close to a spin liquid, but not quite there. Next slide, please. Now, we return to the question, is potassium, ytterbium, selenium-2 a quantum spin liquid? Well, you may say, based on the previous slide, that, well, no, it's not. Its Hamiltonian is within the long-range ordered phase, and you observed long-range order. But I'm going to argue that doesn't mean we can't consider it to be a spin liquid at finite energy scales. And to show why, let's move on to the third tool, comparison to theoretical models. Next slide, please. Now, it's very difficult to do 2-dimensional many-body quantum physics calculations in a generic way. So we collaborated with 2 theorists who did 2 different approaches for this. Christian Batista at University of Tennessee used Schwinger boson theory to calculate what would the spectrum look like of a 2D triangular lattice with the Hamiltonian we got. And then Joel Moore from UC Berkeley used a more brute force approach, DMRG. Next slide, please. The Schwinger boson explicitly assumes the existence of fractionalized quasi-particles in a 2-spin-on continuum. The DMRG, again, is more generic. It includes all possible quantum effects, but it suffers from finite size problems, which is why everything is very broad. But nevertheless, you can compare, you can compare both of these theoretical approaches to the data, and you see very strong resemblance, especially if you squint and compare the DMRG to the data. So next slide. What this means, both of these theoretical approaches, we know why they have a continuum. It's because at finite energy scales, they're looking at quantum spin liquid physics. So this suggests that although potassium, ytterbium, selenium-2 orders magnetically, its inelastic spectrum is dominated by fractionalized spin-ons. But wait, you may ask the question, is it fair to talk about quantum spin liquid physics in a material that's magnetically ordered? Well, I'm going to argue the answer is yes. And the reason why, next slide, is we can point historically to the one-dimensional spin chains. These have been studied for 50 plus years with neutron scattering. Most of them order magnetically, but nevertheless have fractional spin-ons at finite timescales. One example, potassium copper fluorine 3. The nail temperature is 39 Kelvin, but it's a prototype of spin-on physics. You just have to make sure you're looking above some energy scale and you can see it very clearly. All right, so the question we posed, is potassium, ytterbium, selenium-2 a spin liquid? Well, the answer is it's approximate quantum spin liquid. It's close enough that at finite temperature energy scales, it has the spin liquid physics. In other words, the fractional quasi-particles are bound. They exist on short timescales, but they eventually coalesce into very low energy magnons. Okay, so much for this compound. We've studied it very closely, but what about other delafoscites? There's other variants of this material out there. Do any of these come closer to the quantum spin liquid? Well, in this case, we can do some slight modifications looking only at what happens when we swap out the A site element. Cesium, ytterbium, selenium-2 has been studied, and so has sodium, ytterbium, selenium-2. Next slide, please. So the cesium, ytterbium, selenium-2, there's a very nice paper from Oak Ridge and the Paul Scher Institute group. And they fitted the J2-J1 ratio to the high field scattering data and found it's 0.029. The sodium, ytterbium, selenium-2, we didn't find anyone who had fitted this value in the literature, so we did our own experiment, put it in a magnetic field, looked at the plateau phase, and the data, unfortunately, had serious background problems, but it was enough to be able to see the highest energy magnon mode, which is enough to constrain the J2 value. And this said that the J2-J1 is 0.071. Next slide, please. And so if we plot all these values on the same axis, where the x-axis is J2-J1, and the width of these bars is the J2-J1 value and their uncertainty, you can see a trend with the periodic table. As the ion radius shrinks, as you go up the periodic table, the J2 value seems to increase. Now, you may look at this and say, well, look at this. Doesn't it look like the sodium compound is within the spin liquid phase? Well, at first we needed to be careful. Next slide, please. Because the sodium ytterbium compound definitely has more anisotropy in its Hamiltonian than the potassium compound. I won't go into detail for the sake of time, but in the potassium compound, we see at least indications of an out-of-plane plateau, but there's no such indication in the sodium compound. And this, you should see a plateau in both directions if you have a perfectly isotropic Hamiltonian. So the Heisenberg J2-J1 is a less good approximation for sodium, ytterbium, selenium-2. But nevertheless, if you go to the next slide, it is clear that to kind of the 0th order level, you can use the periodic table to precisely tune how close you are to this phase boundary with the quantum spin liquid. So next question that we asked, next slide, please. If you can use chemistry to tune the J2-J1, what about pressure? So we put the potassium compound in a pressure cell here at Los Alamos and measured its heat capacity down to very low temperatures. And we found that as we increased hydrostatic pressure up to around 2 GPa, we saw the ordering transition temperature increase. So the magnetic order is enhanced. We're moving further from the quantum spin liquid phase, which was a bit disappointing. We were hoping that somehow we could be pushed into the phase by pressure. It's not clear why this happens. It could be that we're increasing the interplanar interactions between the triangular lattices. It could be that somehow we're decreasing the second neighbor exchange, or that we're increasing anisotropy in some way that stabilizes order. That's not clear, but it's clear that pressure won't get us the direction that we want to go. All right, so having studied these compounds and identified the trend, we thought, well, we need to take a much closer look at the sodium, ytterbium, selenium-2 compound. And so we did this. We have a paper that's currently on the archive. It's been there for a couple months, where we do some more measurements. Next slide, please. And the key measurements that we reported, we measured the specific heat, the neutron scattering and zero field, and the AC susceptibility. So if you look at, oh yes, I need to acknowledge the paper that kind of made us interested in this whole project to begin with came from Peng-Cheng Dai's group, where they measured a sodium, ytterbium, selenium compound on CNCS. Unfortunately, their material had some 3% site mixing, which in the quantum spin liquid world is sometimes enough to wreak havoc on your ground state. And so we wanted to try to look at, do we see the same sort of thing when we look at a cleaner sample? So next slide. And so we worked with some chemists, most notably Haidong Zhu at University of Tennessee, and he grew us a cleaner sample. Well, honestly, what we hope is a clean sample, but we don't have the most clear evidence for this. No site mixing is visible in the X-ray scattering. But if we look at the heat capacity, it's shown here on the left. This is the red data is from our compound in two different measurements. And the gray data points are from other compounds reported in the literature. This shows a bump at around 700 millikelvin that is not present in the 3% disordered sample. And so it indicates a kind of correlated phase that is emerging, possibly an indication of higher crystalline quality. And if we compare this data to the potassium compound plotted on the same axes, you can see that there is a difference. The potassium compound has a magnetic order transition, but also the heat capacity bump is lower in the sodium compound. So we go, next slide, please. So we tried to be more quantitative about this. We compared the data scaled by J1 to thermal pure quantum, which is an exact diagonalization technique, simulation of 32 sites, just to see, is this trend with the heat capacity consistent with higher J1, J2 values? The short answer is yes. In the theory, if you increase J2, you get a lower maximum in heat capacity. You also get more low temperature heat capacity, and we see both of these things. So this is consistent. Yes, the sodium version has a larger J2, is closer to the spin liquid. Next slide, please. So the next thing we wanted to do is measure the inelastic neutron scattering. And so we did this on CNCS, and we found a much sharper spectrum. The data and the background are shown on the left panels. The data minus background is shown on the right. And you can see, again, a continuum with a well-defined lower boundary. Next slide. And just as a sanity check, we compared this with some of the matrix product, or in other words, DMRG calculations coming from Joel Moore's group. But this time we asked them to add some planar anisotropy, because this seems to be there in this material. And in a rough way, you can see that, yes, we see a pretty close resemblance to what the theory predicts. Next slide, please. We then did our entanglement analysis again, doing the QFI integral. In this case, we found QFI is 2.3 for sodium, ytterbium, selenium 2, which is lower than what we saw in the potassium compound. Next slide, please. And so this actually, you might think, oh, it's a lower quantum entanglement, it's less of a spin liquid, but actually, again, remember that the QFI seems to be most associated with the quantum critical point. And so we'd expect it to be maximal and on the boundary between magnetic order and a quantum spin liquid. Because in the quantum spin liquid, the spectral would start to be distributed around the zone boundary in the Berlin zone. So observing a lower QFI is actually consistent with it being within the spin liquid phase. Next slide, please. All right, and the last data set that I'll show in this talk is also the most intriguing and provocative and controversial. We measured the magnetic susceptibility of the sodium crystals at the Tallahassee Mag Lab in the 18 Tesla dilution refrigerator. And we simultaneously mounted two different sodium crystals, one with the field along A, one with the field along C. And just for sanity, we put in a potassium compound just to kind of double check that what we're doing is making sense. And so if you look at the field dependence, you see an in-plane magnetization plateau, no plateau out of the phase, out of the plane, which indicates planar anisotropy. But the most intriguing result, next slide, please. If you look at the very low field temperature dependence, there's a sudden drop in susceptibility at around 23 millikelvin. And this occurs both in plane and out of the plane. Next slide, please. We measure the frequency dependence. We have to use only very low frequencies here because we're at really, really cold temperatures, so we can't risk heating up the sample. But to within what we can measure, there's no frequency dependence. So this is not a glass freezing transition. And intriguingly, we don't observe any such susceptibility downturn in the potassium compound that, again, was measured at the same time, the same cryostat, same temperatures, same fields. So this is not an experimental artifact. We've actually since remeasured it a couple times in the same machine, and we find the same thing no matter which sodium crystal we use. We see the susceptibility downturn. So the question is, next slide, is this a magnetic phase transition or is it a gap? Because in susceptibility, both of these would look pretty similar at such low temperatures. Is this the long sought magnetic order that we thought might be there? It's just at really low temperatures. Well, we don't have a conclusive answer, but from what we've measured, we believe it's a gap. And there are three reasons for this. The first is the isotropy. The drop in susceptibility is qualitatively the same along the A direction and along the C direction. Magnetic order, antiferromagnetic order, usually produces a different response depending on what direction of the field you use. The second reason is magnitude. The drop in susceptibility is more than 5% of the value, and this is without a background subtraction, which is pretty tricky to do in this particular machine. And so a transition temperature, 23 millikelvin at 1/250th the bandwidth, would have to be a really tiny feature. We would not expect such a dramatic effect in a bulk property measurement at such a very small fraction of the bandwidth. And third, fine tuning. And this argument was given to us by Christian Batista. For a two-dimensional triangular lattice, if you look at the scaling exponents that are expected, the nail temperature should drop off with J2 by a square root, such that when you get close to the transition temperature, it becomes, the phase boundary line becomes almost vertical with temperature, meaning that a 23 millikelvin transition means that the J2 value has to be really precisely tuned to the critical J2. And so to me, it's much easier to believe that this compound is lying within some extended phase than it's fine-tuned to a really precise value. And so for that reason, it's easier to believe that this is a gap. Next slide, please. Oh, yeah. So what does it mean if it is a gap? Well, if this is really a gap that we're looking at, and there's no magnetic order that any measurement has shown, this system is not within the 120-degree ordered phase because that's a gapless phase, and is instead within the quantum spin liquid phase. This is also information about what kind of quantum spin liquid it is, because it's not a gapless spin liquid. For example, the U1 Dirac spin liquid, which certain theorists have proposed as the spin liquid of this material, is ruled out if this measurement is really a gap. So what possible options are left? Well, there's three options we found in the literature that have been proposed by theorists, different phases that would have a gap: a Z2 quantum spin liquid, a valence bond crystal, which is not really a spin liquid, but a frozen configuration of singlets, and a chiral spin liquid. So next slide, please. So the Z2 quantum spin liquid of these three is the only one that should have no phase transition at finite temperature. The valence bond crystal and the chiral spin liquid both have finite temperature phase transitions. So this on its own is evidence in favor of the Z2 quantum spin liquid. But also we can look at theoretical simulations. You can sort of simulate the Z2 quantum spin liquid with Schringer boson simulations. Johannes Canola and his group simulated what a valence bond crystal would look like, starting from a failed U1 spin liquid. The data are shown on the bottom. Next slide, please. And you can see that the best match with experiment is definitely found with the Z2 set of assumptions. And that, combined with the fact that we observe no finite temperature transition, means that of the candidates that have been proposed, the RBB, i.e. Z2 spin liquid, is the most consistent with the data that we have. All right, so with this, we can go on to the conclusions. Next slide. They are with the 3 points that I gave to you at the beginning, and hopefully now you understand the reasoning behind why we say these. The first is potassium, ytterbium, selenium-2 is an excellent realization of the Heisenberg triangular lattice model with a second neighbor exchange, and is close enough to a quantum spin liquid to host spin liquid physics. We can swap out the A site element and use chemistry to give us control over J2 over J1. And finally, the sodium compound appears to be a gapped quantum spin liquid, with albeit a really tiny gap, but this still allows us to tentatively say that this is a Z2 spin liquid. And I think this is really exciting because the fact that we have a series of compounds that we can investigate that all have a clear trend gives us a lot more confidence in the final results than if we were looking at any one of these compounds in isolation. Systematically tuning towards a quantum spin liquid seems to be, in my view, one of the best ways to convince yourself that you're seeing the real thing. So last slide is the next one. So the broader implications of this work, I've at least convinced myself, and maybe you have been as well, is that quantum spin liquids do exist in nature. We seem to have found one, and it's not true that in nature they always fail and become something glassy. And second, we've outlined a protocol for their existence. By using these many different approaches and being systematic, we can really have a confident answer to this question: is a given material a quantum spin liquid? So thank you very much. If you want to know more, I point you to these 3 papers that are listed on the bottom, where we give more details about all this work.
Okay, thank you, Alan. Yeah, very, very interesting talk. Yeah. So let me, I guess maybe I should ask, any people have questions for Alan? So let me, before anyone else raise, let me ask you a question. So in terms of, disorder has always been deemed to be sort of a issue, right? In terms of, right. Do you have actually, systematic measurement to actually show the differences in, disorder between these 3, classes of compounds?
No, that would be a really great study to be able to do.
Because sodium, potassium, and cesium, sort of known to be volatile, right?
right,
so 5%. Right. So you haven't, I guess, characterized how much disorder you have in your sodium.
We can say it's less than 1%, but that's still not satisfying to some people. So it is difficult to characterize the disorder here, but you hit the nail on the head. Someone does need to do a systematic study of disorder and find out what are the real consequences for the properties that are measured.
The other question, yeah, go ahead. I'm sorry.
I was just going to say I'm biased because I spent several years investigating this other spin liquid candidate, ytterbium titanate, which people thought was a spin liquid until they made really, really clean samples, and then they found it orders magnetically, and just 2% disorder is enough to destroy the ordering transition that is there in the clean sample. So that is kind of my personal reason why I'm so cautious about these issues.
Okay. Now, the other question I have is that, typically, people would argue that you see the sort of a spin liquid, one of the ways of sort of chasing down the effect disorder is to basically, completely polarize it. So you couldn't completely polarize it in this, 112 compound. I guess my question is, for in the intermediate polarized state, like, up, down state, are your spin waves sort of resolution limited, or they're broader than the expected resolution?
Yeah. So the lower energy,
you showed the data, right? It wasn't very clear to me.
Yeah, you can look at the data. It's back on slide. I can give you the number. Right. Slide 36. The low energy magnons are resolution limited, but there's this higher energy mode, which Andreas Lauschli at PSI, he did a theoretical study of this and showed this actually a 2 magnon bound state kind of effect. So keep going. This is the sodium compound. But yeah, so the low energy magnons seem to be resolution limited, and the high energy stuff includes these 2 magnon effects that the linear spin wave calculation we did not include. So to within, the resolution, we can say this compound does have sharp modes. But of course, the best would be to go to the saturation field at 12 Tesla, but we couldn't get to 12 Tesla on CNCS, so we had to settle for what we could get to.
I see. As far as I know, there's no measurement, right? At least no neutron measurement for any of the 122s that can, that went to the fully saturation field, right?
No, that's because you need something, depending on which compound it is, you need something above 10 Tesla. And there's not many facilities that can do that for a cold spectrometer.
Okay. But so you basically think, within sort of your measurement, at least one of the bands is sort of basically resolution limited. Would you be convinced if someone shows you the data that's completely resolution limited, then you say the disorder? For any chemical compound, right, disorder is, in my point of view, almost unavoidable, right?
Yeah, so this is the tricky thing. No one really knows why the quantum spin liquids are so sensitive to disorder. Like, this is not fully explained. For a conventional magnet, I would say, yeah, that would be convincing. Show me a resolution limited mode. But I think to to say anything with confidence here, someone needs to really figure out why it is that tiny disorder seems to have such dramatic effects.
Okay.
So, Igor, I see you have a question.
Yeah, actually, it's a remark. I pasted it in the chat as well concerning the little gap. I mean, it's a very interesting question. There is only 14% of ytterbium-171, but it is there, and it has spin 5 half on its nuclei. So.
Yeah.
And in the presence of nuclear spins coupled to electronic spins, this is sort of a old known effect. A little gap would be generated, and that gap would grow, on the nuclear spin temperatures, really low temperatures. We have considered that with Svellik for spin half chain. Essentially, spin half chains are spin liquids, as you know, and many of those have nuclear spins, which are actually coupled. So what happens is that electronic spectrum gets a tiny gap generated. Its soft mode behavior gets overtaken by nuclear spins, but they have no magnetic moments, right? So do not contribute to susceptibility.
So this is something we considered in the archive paper, and we talked about this possibility. Based on our estimates of the hyperfine exchange, that effect for ytterbium should be another order of magnitude weaker in energy. And secondly, we don't see such a gap induced in the potassium compound, which is the same. So if this were a gap from the nuclear hyperfine, I would expect to see it in all the variants, but we only see it in this one.
Not in the ordered one, because their susceptibility is dominated by the ordered moment.
Okay. So this is...
That's a good point.
Then there would be something else. Yeah.
No,
okay.
Here, susceptibility is completely coming from fluctuations, and so if you gap them, you will get it. You will be very sensitive to gapping.
Yeah. So in principle, that's possible. Still, you should look at our paper. But our estimate, and we tried to estimate, is that like this gap for ytterbium should be at like 2 more Kelvin.
I think it actually warrants, you can ask Batista to consider it following the trail of what we did with Svellik for spin half chain. I mean, it's a solvable problem. And experimentally, one can perhaps ask someone to do NMR on ytterbium-171, because that would be seen in NMR.
Yeah. So yeah, I should say we're pursuing this, but NMR and dilution fridge temperatures at such incredibly low temperatures is not so easy.
I see. That's actually a good point. So can you actually, I mean, Igor, do you actually expect the nuclear order? I mean, can you see diffraction?
Not order. It's funnier than that. I think what would happen is that nuclear NMR signal would be wiped out, because nuclear spins, essentially in these situations, they overtake the low energy behavior of the electronic spins. In other words, they will form a little continuum separated by a little gap from the gapful.
So if you do neutron scattering, then I mean, assuming you can have such a good resolution, would you expect to see a gap then? You wouldn't, right?
Well, yes, we will see a gap. I think that would be 2.1 microelectron volt gap that Alan was referring to.
Oh, but this gap you think has nothing to do with electronic properties, but rather it's induced by nuclear spin.
So what nuclear spins do, they basically push up the electronic spectrum, and then they form their own little nuclear NMR spectrum, and that NMR spectrum is actually sort of reflective of what would electronic spectrum be. This has been studied. I mean, I pasted one of the papers, but it has been studied in manganese type systems in quite great detail.
Okay, that's interesting.
Yeah,
I mean,
these are all systems where the percentage of nuclear moments is much, much higher, though. So that's another big important difference.
Yes, but in manganese, of course, it's 100%, but then it also happens at an order of magnitude higher temperature.
Right.
So what is the percentage of ytterbium that has the nuclear spin?
14%. 14% of ytterbium, which are 171. Those are the ones that, quantum information science people who are doing NMR quantum information qubits, those are the ytterbiums they are using. So actually, it's a very interesting question.
But then you can, if you use the isotope, different isotope, then this wouldn't happen, right?
Yeah, that's another possibility. If you make it of ytterbium-171 or without ytterbium-171.
Interesting. That's an interesting idea. Okay. Yeah. Any other question for Alan? It's a really nice talk. I mean, I quite enjoyed. I quite enjoyed it. I mean, you made a pretty nice story of this systematic study, which is very important. Yeah.
I agree. I forgot to say that. Yeah. Thanks a lot, Alan. Great talk.
Yeah.
Well,
Okay.
thank you.
Are there more questions? Okay. If not, yes. Thank you. Yeah. Thank you, Alan.
Thanks very much.